Enzymes function as biological catalysts to increase the rate of nearly every reaction in biological systems. To understand how enzymes work, researchers often turn to a field of biology called enzyme kinetics. Kinetics studies the rates of enzyme-catalyzed reactions and how these reactions are affected by different substrates, concentrations, and other influencing factors. The foundation of all enzyme studies is the Michaelis-Menton equation derived by Leonor Michaelis and Maud Menton in 1913. In this video, we will use one of the most important enzymes in American society, Hotdog-Ase, to demonstrate the variables expressed in the Michaelis-Menton equation and how they are determined experimentally. VI is the initial velocity of the reaction. This is usually measured through spectroscopy, but we will measure it today as the number of hot dogs per minute. We begin the experiment with a low substrate concentration. Hotdog-Ase's ability to catalyze the formation of hot dogs is greatly limited because it must find a weenie before it can catalyze product formation. At this low substrate concentration, the rate of the reaction is very low. Note that the rate of hot dog formation is limited by the time required for Hotdog-Ase to bind its substrates. Now let's gradually increase the number of buns and weenies and measure the rate of hot dog formation as catalyzed by Hotdog-Ase. At the bottom of the screen you can see that the rate of hot dog formation increases significantly as the number of weenies available to Hotdog-Ase increases. As the number of hot dogs and weenies available to Hotdog-Ase continues to increase, the enzyme is no longer wasting any time searching for its substrate. In other words, the enzyme is saturated with substrate. At this point, the rate of hot dog formation becomes nearly constant, depending only upon the rate of enzyme catalysis. This constant, high rate of product formation appears to be approaching 26 hot dogs per minute. Let's look at how this information looks on our Michaelis-Menton plot. On the x-axis we have the substrate concentration, or in our case the number of weenies in the cell, and on the y-axis we have the initial velocity that we just measured. The graphed results of Hotdog-Ase catalyzed formation produces a rectangular hyperbole, meaning it goes up fairly steeply and then levels off as the line approaches an upper limit. This upper limit represents Vmax, at which point the limiting factor is the rate of enzyme catalysis. In other words, as at Vmax, the rate depends only upon Hotdog-Ase's ability to put the bun and the weenie together, and no time is wasted searching for substrates. The only variable that we are now missing in the Michaelis-Menton equation is Km. From the Michaelis-Menton equation, we can say that Km is simply equal to the concentration of substrate that produces half the Vmax. Analysis of this experiment is made easier by taking the reciprocal of both the concentration of substrate and initial velocity. This is known as a Lineweaver-Burk plot. Note that in the Lineweaver-Burk plot, Vmax is equal to the inverse of the y-intercept, and Km is equal to the negative inverse of the x-intercept. Remember, better, tighter, faster enzymes have lower Km values and higher Vmax values. Now let's consider the effect of adding a competitive inhibitor. Enzyme inhibitors are compounds that interfere with an enzyme's natural catalytic activity. Competitive inhibitors bind to the active site of the enzyme, competing with the substrate. Many competitive inhibitors resemble the natural substrate but are not capable of undergoing the catalyzed reaction. Enzymatic activity is therefore forced to stop. We will use a whiteboard marker as the competitive inhibitor for Hotdog-Ase. Let's start again at a low concentration of weenies. As Hotdog-Ase moves about the cell, the chance of picking up a marker is equally as probable as picking up a weenie. This greatly slows down the rate of enzymatic reaction. But what happens if we increase the concentration of substrate? As the concentration of weenies increases, the probability of binding a substrate rather than a marker inhibitor increases as well. That is, by increasing the concentration of substrate, the competitive inhibitor is outcompeted for the active site of the enzyme by the substrate. Now we plot the initial velocity of the Hotdog-Ase catalyzed hot dog formation with the marker inhibitor on the same graph as the uninhibited reaction. Since the y-intercept is the inverse of Vmax, our graph seems to be telling us that the inhibited and uninhibited reactions have the same maximum velocity. That is actually true. Because the effect of competitive inhibitors can be diluted by adding excessive substrate to the reaction, the enzyme can still reach its normal maximum velocity. However, as you might guess, the amount of substrate needed to achieve Vmax is much greater in the presence of an inhibitor. We would also expect the Km of an inhibited reaction to appear higher, since Km is the concentration of substrate needed to achieve half of Vmax. The x-intercept of the inhibited data series is different from our uninhibited data series, meaning that from the graph it looks like the competitive inhibitor produces a new Km for the reaction. This is a bit of an illusion. The Km is a constant of the enzyme and it does not change. The x-intercept of an inhibited reaction produces a value called the Km apparent because it appears to be a new Km. This concludes our introduction to enzyme kinetics. We would like to thank Brother Steve Christensen for his inspiring lessons linking American cuisine to the study of life. We would also like to thank Major League Baseball for providing the optimal environment for Hotdog-Ase catalyzed formation of the hot dog.